Problem 4980. I'm going to prove the Cauchy-Schwarz identity. Cauchy-Schwarz identity states that absolute value or magnitude, or well, in this case, absolute value of scalar product of two vectors is less than or equal to the product of their second norms, vector u and vector v. This is one of the simplest forms of Cauchy-Schwarz identity, Cauchy-Schwarz. And it's quite useful in linear algebra and in calculus, and it's often used. So how to prove that? Well, in order to prove this, we have to use one of the well-known theorems in linear algebra and vector analysis. This theorem states that the square of the vector, which is essentially the scalar product of the vector itself, is always greater than or equal to 0, and it equals to 0 if and only if the vector itself is 0 for any vector u which is in vector space and dimensional vector space over the field of real numbers. Let's say we have a vector t u plus v, where t belongs to, this is just a scalar from the real field. Then, based on our inequality, tu plus v square is greater than or equal to 0, which is equivalent to saying that tu square plus t2 tu v plus v square is greater than or equal to 0. Nice. What is this? So this is essentially t second norm square. This is second norm square t square plus t u uv t uv plus v second norm square greater than or equal to 0. We can replace these variables and substitute them with a, b, and c, and we're going to get quadratic equation or inequality here, which is a t square plus b t plus c greater than or equal to 0, which means our discriminant of this system is less than or equal to 0, because this parabola is always non-negative. That means it has only one positive real root, or it may not have any roots at all. So for this case, we have discriminant is less than or equal to 0, which is equivalent to b squared minus 4ac is less than or equal to 0, where b is 4uv square minus 4 the second norm u square and the second norm v square less than or equal to 0. Then uv square is less than u second norm square v second norm square. So what is that? This is essentially x square less than y square. And we know that this inequality is equivalent to x. Absolute value x is less than or equal to absolute value y. So taking the square root here, we can show that uv is less than absolute value of uv. I apologize. The absolute value of uv is less than or equal to second norm u and the second norm v, which are absolute values and they're always positive. So, and this is the exact definition of Cauchy-Schwarz inequality. So we basically prove that. But now you may wondering how to actually show that x squared is less than y squared, how to show that this inequality, how to prove this inequality is equivalent to this one, to the absolute values. Well, that's pretty simple. We already know that square of the number is the square of its absolute value, and the same for y, right? It is the same thing. So we basically can say that x square, y absolute value square, this is equivalent to x square is less than or equal to y square, and then we can say that x minus y, x plus y, because it's a known identity, right, which is equivalent, and then this part is always non-negative, so we only need to show that this one minus absolute value y is less than or equal to 0, which is equivalent to is less than to y.